Hello, and welcome to Thermochemistry number 2. Today we're going to talk about activation energy. Activation energy is the minimum energy that colliding particles must have in order to react. Remember when we were talking about collisions, how there's something called an activated complex. Well, in order to form an activated complex, in order to break the bonds, it requires energy. And that energy is called activation energy. So for our reactants, in order to break those bonds, it's going to require energy to form the activated complex, which is also called a transition state. The activation energy is the barrier that reactants must overcome before products can form. It is usually not necessary to break all the bonds in the reactants in order to form products, so the activation energy is less than the sum of the bond energies of the reactants. I have an enthalpy diagram for the combustion of methane. The combustion of methane is an exothermic reaction. The energy of the products, as we can see on this diagram, is lower than the energy of the reactants. However, methane does not spontaneously ignite. Your farts don't just light on fire. That doesn't happen. You need a spark. You need energy. You have to put energy in the system, right? So the energy comes from an ignition source. And to overcome that, to form the activated complex, that allows the atoms to rearrange to form carbon dioxide and water. And because the energy of the products is less than the energy of the reactants, the overall reaction is exothermic. Heat is released. If you light your fart on fire, your fart's going to be hot. Enthalpy of combustion is the enthalpy of the reaction for the complete burning of 1 mole of a substance. The delta H for the combustion of methane, as you see, is negative 890 kilojoules per mole. Remember, in exothermic reactions, enthalpy is going to be less than 0. If this was an endothermic reaction, the enthalpy would be greater than 0. Representations of enthalpy. Enthalpy diagrams can be used to visually represent the changes in enthalpy for reactions. Another way to represent an enthalpy change is by writing it as part of a chemical equation. And we call these thermochemical equations. It's just enthalpy written as a product or reactant. With the enthalpy written as a product or reactant, we can also write the enthalpy change as a separate algebraic equation to the side of the chemical equation. And I'll show you right here. Okay, so in this exothermic reaction, calcium oxide is an ingredient in cement. It gets hot when it's mixed with water. That just happens spontaneously. When you mix calcium oxide with water, it gets hot. The energy is released. In such a reaction can be shown as a down arrow in an enthalpy diagram, like this, or written as part as a thermochemical equation, like this. So as we see, we have a down arrow in this enthalpy diagram. It's showing us the energy is being released. The energy is going down. Because our products have less energy than reactants, we know it's exothermic. Our delta H should be less than 0. And it is. It's negative 65.2 kilojoules. Now we can also model this as a thermochemical equation. So we write our balanced equation like this. Calcium oxide reacts with liquid water to form calcium hydroxide solid, which is cement. And we're releasing 65.2 kilojoules. Now, right here, this is written as a positive enthalpy, and that's because it's on the product side. So it's okay because it's okay. But if you're writing it as a delta H, we would write it as negative because it's telling us that it's exothermic. Because this is written on the product side, the heat is being released, we know it's exothermic. So when we write them as thermochemical equations, they're always going to be positive values. However, depending on what side of the reaction it's on, whether it's on the reactant side or the product side, that's going to tell us if it's endothermic or exothermic. So let's look at our next example. Our next example is an endothermic reaction. Sodium bicarbonate used in a muffin batter requires energy, heating in the oven to produce CO2 gas. Sodium bicarbonate is also called baking soda. It allows those little bubbles to form. Those bubbles in your breads and cakes that make it like airy and delicious is carbon dioxide gas. But that doesn't just happen, it needs heat. You got to add energy into the system to make that reaction happen, which is your oven. It also causes the batter to rise. You know when you pour batter into a muffin tin, you pour it below the muffin tin, but when you take it out of the oven, those muffin tops are above the muffin tin. That's all thanks to the sodium bicarbonate. It allowed that muffin mixture to rise. When energy is absorbed, it can be shown as an up arrow. Do you guys see this up arrow in the diagram? Or we can also show it as written in a thermochemical equation on the reactant side because we're adding energy into the system. The energy is being added into the system, so it has to be on the reactant side. So we can look at this here. This is sodium bicarbonate, okay? And then we're adding energy into the system, so our products are at a higher energy level than our reactants. That's how we know it's endothermic. Now over here, we can see that our energy is on the reactant side. Our overall delta H, our enthalpy of the reaction, is 136 kilojoules. Okay, so using enthalpies of reactions, we can use a little bit of stoichiometry. We're going to add that in from what we were doing before we went on this crazy break. And we're going to add it into this new stuff, so you're now a chemistry genius. So we're going to use enthalpy of reaction to calculate enthalpy change. Here is our question. The production of iron and carbon dioxide form iron 3 oxide and carbon monoxide. It's an exothermic reaction. How many kilojoules of heat are produced when 3.4 moles of iron 3 oxide reacts with an excess of carbon monoxide? Okay, so first we start with a balanced reaction. I gave it to you. You're welcome. Now it told us it was exothermic. So that means that our enthalpy, our heat, should be on the product side. And it is, right? Because our heat's being released. It's getting hot in here, you know, in the words of Nelly. So we got to put that on the right side. Now, the strategy I like to use when I do this is I create a table of knowns and unknowns. So what do I know? Let's start with the given. Let's always start with the numbers found in the problem. We're not doing new things here. We're doing it the same way we've always done it. So let's look at the word problem. Let's look for numbers. Oh, look, there's some numbers. 3.40 moles of iron 3 oxide. So we know that. That's something we know. We also know the enthalpy, and the enthalpy is 26.3 kilojoules. Okay, what we don't know is what is the enthalpy for this reaction if we have 3.4 moles. What's that? So, we have to do a little bit of stoichiometry, and you can do it. You got this. You're gonna be great. Okay, so we're gonna calculate and solve for our unknown. That's the first step. We're gonna use the thermochemical equation to determine the conversion factor relating kilojoules of heat and moles of iron 3 oxide. So look, we have 26.3 kilojoules, and how many moles of iron 3 oxide do we have? Let's look for the number in front of the equation, our coefficient. I don't have a number here in this balanced equation. If I don't have a number, that means I have 1. So in my conversion, in my ratio, I'm going to put 1 mole of iron 3 oxide. Okay. So once we found out our ratio, we're going to use dimensional analysis to solve for the enthalpy. So we're going to always start with the number in the problem, right? That always goes into our box 1. This is exactly like the 3-box model. So we're going to start with the number in the equation in box 1. Okay? Box 1 and 3, the units must agree, right? So 3.4 moles of iron 3 oxide, and then using our balanced equation, which was right here, we have 1 mole of iron 3 oxide. And we had that ratio, 1 mole of iron 3 oxide contains 26.3 kilojoules. So as we see in box 1 and 3, our units agree, so they're going to cross cancel. Next, we are going to multiply boxes 1 and 2. So we're going to put into our calculator or your phone calculator 3.40 times 26.3. That's going to give you 89.42, and you divide by 1, and that's still 89.42. We're going to use our units for box 2. Box 2, our units are new. So our answer is 89.42 kilojoules. Okay, more practice. Now to do these practice problems, I want you to get out a piece of paper. I want you to try these ones on your own. So I'm going to read you the problems, and then I'm going to take a pause, and then I want you to pause this video. Give yourself time to work through these problems. You might have to scroll back to a previous portion of the Thermochemistry number 1 video to get a data table. So you're going to need that data table. You can also find the data table online by just Googling it. You can look for an enthalpy table. Just Google that, and it'll pop right up for you. So you would need that one for number 1. Okay, so number 1, the average bond enthalpy for a carbon-oxygen double bond is 799 kilojoules per mole. And the carbon-hydrogen single bond is 413 kilojoules per mole. Using these values, in the values from slide 19, which is found in Thermochemistry number 1 video or on Google, I want you to calculate the overall change in enthalpy for the following reaction and tell me if the reaction is exothermic or endothermic. Okay? And I balanced the equation for you, so you're welcome. We can do a quick check. 1 carbon, 4 hydrogens, 2 times 2 is 4 hydrogens, 4 oxygens, 2 plus 2 is 4. Beautiful. Number 2, calculate the amount of heat released when 3.56 moles of ammonia is produced from nitrogen gas and hydrogen gas according to this reaction. So number 2 is very similar to the problem that we did on the previous slide. For number 1, that one's going to be similar to a enthalpy diagram that I showed you a little bit ago. And what you're going to have to do is you're going to have to figure out how many bonds are in CH4. Hint, when in doubt, draw it out. So draw out the Lewis structures for all of these molecules. And then you're going to count how many bonds are they? What kind of bonds are they? And you're going to want to use, we'll go back way far. Let's go back to this average bond enthalpy diagram. So you can use this to help you with question 1. So I gave you the carbon-oxygen bond, and as you see, the carbon-oxygen double bond is 799 kilojoules. And I also gave you the carbon-hydrogen bond. That's one's 413. So I want you to look over here, and you're going to have to figure out what other kind of bonds are in the molecules. And you're going to have to calculate how many of them do you have. And I want you to remember, to calculate the enthalpy of a reaction, you're going to add up the enthalpies of the products. You're going to add up the enthalpies of the reactants, and then you're going to subtract them from the enthalpies of the products. Also remember, the enthalpies of products when you're making bonds, it's endothermic, right? So when you're making, it's exothermic. I'm having a hard time right now. It's exothermic, so those enthalpies are going to be negative. So your reactants are going to have positive enthalpies, but for your products, you're going to have to change the sign. Those are going to be negative enthalpies. So this question's a little bit tricky, but I think you can do it. Okay, so we're going to go right here. And at this point, pause your video so you can do these problems, because the next part is going to be the answers, and I want you to try these practice problems before you see the answers. So pause the video right now. Okay, I hope you had a fantastic time doing those 2 practice problems. For number 1, it's negative 808 kilojoules. How'd I get that? Okay. Well, what you're going to have to do for that is, in methane, CH4, we have 4 CH bonds, right? So you're going to have to add all of those up. Then you're going to have to add that to 2. We have 2 moles of oxygen gas. So oxygen gas, if you drew out your Lewis structure correctly, you would remember that oxygen gas is the Brinkelhoff twin, and it's an oxygen-oxygen double bond. Because we have 2 moles of that, we're going to multiply that enthalpy number for the oxygen-oxygen double bond by 2. Okay? And that's going to give you, so for the carbon-hydrogen bonds, that's 652. And for your oxygen-oxygen double bonds, that's going to be 990. So if we add that together, is going to be 2,642. Okay, now we have our product side. And our product side, we have to change our sign. So for carbon dioxide, if you drew out the Lewis structure, you would remember that carbon and oxygen is a double bond. And there's 2 of them in carbon dioxide. So carbon-oxygen double bond is 799. I gave that one to you. So you would go 799 times 2 in your calculator, and you would get 1,598. But it's exothermic because it's a product, so it's negative 1,598. Then you're going to do water. So water is comprised, for each water molecule, you're going to have 2 oxygen-hydrogen bonds. Okay? And each oxygen-hydrogen bond is going to be negative 463 kilojoules. You have 2 water molecules. So that means you have 4 of those bonds all together. So 463 times 4 is 1,852. But it's a product, so you're going to have to throw a negative sign in front of it. Okay, so how do you solve this problem? Well, we're going to do the enthalpy of our CH bonds in ammonia, so it's 1,652, and we're going to add it to the enthalpy of our oxygen-oxygen double bonds, and that's 990. Altogether, that's 2,642. Now we have to subtract our products. So we're going to go 2,642 minus 1,598, and that's taking into account our carbon dioxide bonds. And then we're going to subtract 1,852, and that's taking into account all of our oxygen-hydrogen bonds. When we do that, we get negative 808 kilojoules. Because it's negative, it's exothermic. Heat is released, which makes sense because it's combustion. Okay, number 2. How do we do that one? Okay, so I'm going to go back for a sec. So first, we want to make a ratio. So we have, how many moles of ammonia do we have? We have 2 moles of ammonia. So we're going to need to use that in our box 3. So we always start with what's given, box 1. Box 1 is a number that comes from the word problem, 3.56 moles of ammonia. Box 2, our units are new, and that's going to be our enthalpy, 92.4 kilojoules. Box 3, our units agree, right? And that's going to be the same as box 1. So that's what we're going to throw in that 2, because we have 2 moles of ammonia. So we multiply boxes 1 and 2. We have 3.56 times 92.4. And then we're going to just divide it all by 2. And that's going to give us 164. Plus a little extra. Well, we go by our significant digits. We have 3 significant digits in our problem. So then our answer needs to have 3 significant digits. So we're just going to round. So 164 kilojoules of heat is released. And that's it, you guys. You learned thermochemistry, so have a great rest of your day.